Okay, as we work our way through this unit, we've talked about a number of things with regards to bonding. We've talked about ionic bonding, and now we're going to talk about covalent bonding. But to talk about covalent bonding, you have to talk about what we call Lewis structures. Now, we've already drawn Lewis structures a little bit, but what we want to do is go into them with a little bit more detail. Basically, a Lewis structure is going to be a model, and you can use that model to explain a number of things, but what we're going to use it for is to explain covalent bonding. So before we start talking about covalent bonding in too much detail, let's talk about Lewis structures. Okay, first of all, to understand why we use Lewis structures, you have to understand that covalent bonding is a sharing of electrons. When we talked about ionic bonding, we said that it was a transfer of electrons. So when something gave up electrons, it got a plus charge. When something took electrons, it got a minus charge. The bond then was that force of attraction between those opposite charges. Well, covalent bonding is a little bit different. What you have is a sharing of electrons. So instead of the hydrogen giving up that electron and another hydrogen taking that electron, what the two hydrogens do is come together with their valence electrons, and they share those valence electrons in their orbitals. And we'll talk a little bit about how those orbitals act, but for now, what we can say is those orbitals overlap. Those electrons are shared between the orbitals, and that is what holds the two atoms together to form a covalent bond. As we talk about Lewis structures, you might want to come back to this slide to see the rules for determining how to draw a Lewis structure. So as we do this, I'm going to go through these three rules. Alright, so let's just do an example of a simple compound, carbon with 4 hydrogens. That's actually the structure for methane, but what we're going to say is it's just carbon with 4 hydrogens. Okay, so the first rule says sum up the valence electrons for all the atoms. So if you look on your periodic table, you'll see that carbon has 4 valence electrons. Hydrogen has 1 valence electron, but since we have 4 of them, we're going to multiply 4 times the 1 valence electron for each, so 4 times 1. So we have a total of 8 valence electrons in the compound. It says use a pair of electrons to form a bond between each pair of bound atoms. All right, so the next thing you need to do is draw a structure that makes sense. And there's a few hints that you want to use. First of all, you're usually going to have a central atom. In other words, you're going to have an atom and then things around that atom. In general, carbon will always be the central atom if it's present. If it's not, what you're going to do is develop a little bit of intuition about what the central atom will be, and we'll go through that as we do the examples. So I've drawn my structure as carbon, with carbon as the central atom, and then I draw the other elements around it. And you always want to go in symmetrical angles if possible. So for example, there's 4 things around carbon, so I'm going to put 2 of them in the horizontal or x-axis if you want to think of it that way, and 2 of them in the vertical or the y-axis. Okay, so what you need to do now is place your 8 valence electrons around the structure. So everything except hydrogen has 8 valence electrons to satisfy the octet rule. Hydrogen, as we know since it's in the first energy level, 2 electrons will satisfy its outermost energy level. So hydrogen only needs 2 around it. So I'm going to put 1, 2, 3, 4, 5, 6, 7, 8. My 8 valence electrons. This carbon can count all of these as its own. 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen can then count the ones that are shared with the carbon as its own. So they each get to claim the shared pair of electrons as their own. Now remember, these are held together in these orbitals, and that's what forms the bond, but we don't draw those. Okay, let's go through a couple of examples, and what we'll illustrate here what we refer to as single bonds. a single bond is one shared pair of electrons. Okay, so first of all, count the total valence electrons. Each hydrogen has one, and there's two hydrogens, so there's two total. Now here we've got hydrogen and hydrogen. We don't have a central atom. There's no way to arrange those other than putting them next to each other. So we have two valence electrons, so all we're going to do is put those two electrons in between the two hydrogens. So they each can claim those two electrons as their own. So this hydrogen has two valence electrons, this hydrogen has two valence electrons, so they form that bond. Another way to draw this is write the hydrogen, a single line, and another hydrogen. That single line represents a shared pair of electrons. And you'll see when we do double bonds, we'll put two lines, or three bonds, we'll put three lines. Okay, let's take a look at the next one. We've got two hydrogens, so that's 2 times 1, plus oxygen has 6 valence electrons, so we have a total of 8. So we're going to put our oxygen, our hydrogen, and our hydrogen. Now here we have a central atom. In other words, you wouldn't draw this structure HHO because this hydrogen can't share electrons on both sides because it can't have 4 valence electrons. Hydrogen can only have 2, so that doesn't work. So if we put our 8 valence electrons, 1, 2, 3, 4, now these two hydrogens each have their 2 valence electrons, so you can't put any more electrons here. So when you have the case of too many electrons, what you do is simply put them on the other side of oxygen. So now this structure would be hydrogen single bonded to oxygen, single bonded to another hydrogen with 2 lone pairs of electrons. The carbon tetrachloride, again, we want to put carbon as the central atom, chlorine, 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 chlorine. Count up the total valence. Carbon has 4 plus 4 times 7, so you've got 28, 32. When you've got a whole bunch of electrons, one thing you might want to do is just put them all around, each having 8, and then see if you have enough electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So as you can see, this compound would be easier to draw like that. When you have an element that has 3 lone pairs around it, you don't have to write the lone pairs. They're implied. So you can just leave those blank like you see here. Okay, now we're going to have a situation where we have double bonds. Okay, we have carbon dioxide, so let's draw the structure. Carbon, oxygen, oxygen. We'll make that carbon the central atom. Count up your valence electrons. 4 plus 2 times 6 is 16. So if you put your electrons here now, like we did, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, we have a problem. This oxygen has 8 around it, which is good. This carbon has 8 around it, which is good. This oxygen now only has 4. 1, 2, 3, 4. Well, that's no good. They need 8. So what we need to do is make double bonds. Now a little bit of a trick here. What you're going to do is take the one that has plenty of electrons, and you're going to share those 2 pairs with the oxygen and the carbon. So then we're going to take those and we're going to put them here, and then we're going to take those and we're going to put them here. So you've got oxygen with 2 lone pairs, double bond, carbon, double bond, oxygen, 2 lone pairs. Now the question might be, well, how did you know how to do that? Honestly, it comes down to trial and error. And what you're going to develop are a few tricks and a few techniques for drawing these, but really the best way to do this is just trial and error until you get it right. All right, O2 is 2 times 6, which is 12. So we put our 2 oxygens. So we've got 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And as you can see, this oxygen here is deficient. So we need to take one of these pairs and share it. So now we've got oxygen, double bond, or I'm sorry, 2 lone pairs, double bond, oxygen, 2 lone pairs. And it works. Sulfur trioxide, central atom, oxygen, oxygen, oxygen. Let's count up the valence electrons. 6 plus 3 times 6 is 24. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Everything is good except this sulfur. Sulfur needs 8. So what we're going to do is take 2 here, get rid of them from there, and move them here. So now this oxygen can claim 1, 2, 3, 4, 5, 6, 7, 8 as its own. Sulfur can claim those 8 as its own. Oxygen, oxygen, and it's happy. So we have oxygen, 2 lone pairs, double bonded to sulfur, oxygen, and oxygen. Now notice, since these oxygens here have 3 shared pairs, we don't have to draw the shared pairs. But since this one only has 2 shared pairs, we have to put them there. Okay, let's take a look at triple bonds now. 2 nitrogens, count up the valence electrons. 2 times 5 is 10. So if we just drew them around, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you can see this nitrogen is deficient. So we're going to take 2, put them there. Now this nitrogen still only has 1, 2, 3, 4, 5, 6. So we're going to take that pair and we're going to put that there. So now we have nitrogen triple bonded to another nitrogen, each of them with a lone pair. HCN, we have 1 plus 4 plus 5, that's 10. This one, the hydrogen can only have 2, and what you're going to find is it's going to have that structure, 2, 4, 6, 8, 10. Okay, here's a situation where you've got 2 carbons and 2 hydrogens. Now remember, you might think, well, the hydrogen could go here or here. Remember, hydrogen can only make 1 bond. So you know, now I suppose you could put another hydrogen over here, but what you would find is that the carbon wouldn't work. So you want to distribute the atoms as symmetrically as possible. And what you're going to find then is that there's a triple bond in between those 2 carbons. Okay, you can also draw Lewis structures for polyatomics. Now remember, the polyatomic acts as a whole with that charge representing the whole unit, not just the oxygen. So if you've got nitrogen, oxygen, oxygen, and oxygen, the only difference here is when you count up the valence electrons. We have 5 plus 3 times 6, which is 23, but since there's a negative charge there, if it's 1 negative, that means there's an extra electron here, so that would be 24 electrons. So you need to put 24 electrons around the structure. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. But since our nitrogen is deficient, we're going to move 2 over there to make it a double bond. And then you can do the last two structures on your own since this vodcast is running a little bit late. And again, you can email me questions to hannonandchemistry@gmail.com and do the practice problems on the site.